Let's look at our notes for this week. Let me see which notes am I doing first. Make sure I got them there. Okay, got our notes. All right, let's look at our notes for this week. I'll put it up on the screen. We're going to work on our rational expressions. All right, focus. Focus. All right. All right, let's go through our notes. Then we'll look at our assignment after that. But let's talk about rational expressions. So a rational expression is a quotient. It's a quotient of two polynomial expressions. That means there's one on top of another. It's like a fraction. You could also say this is a ratio. It could be a ratio of one to another. So this is what we do when we have rational expressions. First and foremost, factor everything that can be factored. That's key right there. Then we simplify and we eliminate common factors. All right, common binomials. So let's just look at a few just to get us started. So if we're going to simplify just a very, very simple rational expression like this, 20x to the 6th over 14x squared. Well, we can simplify first the 20 over 14 because we can divide 2 out of that. 2 over 2 is just 1. So divide it by 1, but it's 2 over 2. So this becomes 10 over 7, right? And so we have x to the 6th over x squared. So that basically is x times x times x times x times x times one more divided by x times x. So we got 6 x's being multiplied together and divided by 2 x's being multiplied together. Well, if you have an x divided by an x, that just equals 1. So that equals 1. We also have an x divided by another x, so that is equals 1. So the bottom is just a 1 because those all canceled out with x's that are on top. So we have x to the 4th over 1. So we just put x to the 4th on the top and multiply the bottom by 1, which means it doesn't change. So this simplifies to 10x to the 4th over 7. Or you can write 10/7 x to the 4th. That's the same thing. Those are equivalent to one another. But we're not going to be working a whole lot with simple ones. We're going to use binomials and trinomials for the most part. So let's look at binomials over here. So the first step, remember, factor everything to be factored. Well, this top, the numerator, we can factor out a 6. It is the greatest common factor. So it just ends up k minus 36 divided by 6 is 6. And then the denominator is k minus 6. So look at that. We have 6 times k minus 6 divided by k minus 6. Well, when you multiply and divide by the same number, that's just the same as canceling each other out. So this just equals 6. It doesn't matter what k equals. This will equal 6. So that's simplified to just a number. We're done with that. Let's look at this. Y plus 8, that's simplified on top. But let's break this out into its factors. Y squared plus 2y minus 48. Well, that's going to factor to y plus 8 and y minus 6, right? Because 8 times negative 6 is negative 48. And 8 plus negative 6 is plus 2. So when we rewrite this, it's y plus 8 divided by y plus 8 as one factor, and y minus 6 is the other factor. So we factored everything that we factored. Now we simplify and eliminate common factors. Well, on top, we have y plus 8. On the bottom, we have y plus 8. That cancels each other out. Y plus 8 divided by y plus 8 is just 1. So these become just a 1. So we have 1 over 1 times y minus 6 is just y minus 6. And that's our answer. That is what this simplifies to. That's what it solves to. These are the same equation. Oh, that's a good thing to look at. Let's look at this. Just occurred to me. Let's graph y plus 8 on as a numerator divided by, and on the bottom we had y squared plus 2y minus 48. All right, we may have to zoom out now. But y squared plus 2y minus 48. For some reason, it doesn't like that.
Okay, so
f of x equals.
As per usual, you have your student notes.
I tried to find it. Oh, f of y. How about that? F of y. There. Now it does. All right. F of y equals y. Since we had y's instead of x's, it wasn't sure what we were trying to do. That's the graph of f of y equals y plus 8 over y squared plus 2y minus 48. Now let's graph what we came up with as an answer. F of y equals 1 divided by y minus 6. Well, look at there. It's the exact same graph. There's the green one, which is the top. There's the purple one. It's the exact same graph, which it should be. If we simplified things correctly, they should be the same graph, right? Because it's the exact same equation. So that's a way to test. If you're not sure, did I properly simplify this? And you're not sure if you got it right, you can graph both of them. Graph that one and graph that one and see if it's the same graph, because it should be. So we factored everything, we simplified them, and eliminated anything that was in common. All right, let's do one over here. First thing we want to do is factor out the greatest common factor. There's a 2, r squared minus r minus 20. So that's factored the 2 out of the numerator. Here we got 8r plus 32. Well, we can factor an 8 out and have r plus 4. Okay, so we factor out the greatest common factor. The denominator is as simple as it gets. 8 times r plus 4. But we can factor this trinomial. Minus 20 and a minus 1 in the middle. So that's going to be 2 times r plus 4 r minus 5. Plus 4 minus 5 will end up at negative 1. Plus 4 times minus 5 is negative 20. Over 8 over r plus 4. All right, what can we simplify? Well, we see again that we've got the same factor on top and bottom. So r plus 4 divided by r plus 4 is just 1. So those cancel each other out. They're just 1. 2 over 8. That's 1 over 4, right? 2/8 is the same as 1/4. So what's left on top? 1 times r minus 5. What's left on bottom? 4 times 1. So that's what that simplifies to. R minus 5 divided by 4. All right, let's do a couple more, because this gets a little tricky. Look, there's a little watch out over here. A minus b divided by b minus a. If we have p squared minus 49, this is the difference of two squares. If we recognize that, it makes it easy to factor, because that's p plus 7, p minus 7. All over 7 minus p. Ooh. We got to be careful there. 7 minus p is not the same thing as p minus 7. Because what if p equals 0? 0 minus 7 is not the same as 7 minus 0. Because this is negative 7, that'd be positive 7. So these are not the same. But we can factor it. If we take this and we factor out a negative 1. Factor out a negative 1. That would give us a negative 7 plus p. I didn't write that very well. Let's move that over a little bit. One more room. If we factor it out, negative 1, negative 7 plus p, we can rewrite that. That's the same thing as p minus 7. I just put the negative 7 first. So if I do that,
Yes.
this can become P
Yes.
plus
Oh, you probably
7
have- there's this,
P
really
minus 7
iconic,
over
visual
negative
of
1 times P minus 7.
fossil that was found.
Now
And
they're the
there's, like, a
same
whole
thing because we factored out negative 1. So this is the same as negative 1 times P plus 7. Since there's just a 1 on bottom, there's nothing left to be a fraction anymore because dividing by negative 1 just makes it a negative. So this is the answer, or you could go ahead and distribute that and say negative P minus 7. These are the same. Negative P minus 7 or negative 1 times P plus 7. All right. Let's see. This one factors the greatest common factor of that. 3a comes out. Oh, there's still the 4 left there. 4a squared. 3a minus 1. We can take a 6 out down here and an a squared. 6a squared. When we take 6a squared out of that, this leaves a, and that a plus 1. So factoring 3a over 6a squared, that just leaves 1 over 2a. This difference of squares. 2a minus 1 and 2a plus 1. And down here we have a plus 1.
So there's obviously a big divide there.
Oh, wait. Yeah, a plus 1 is all we got left down there. Or minus 1. Yeah. So that's not the same. A plus 1 is not the same. I mean, it's not the same as 2a plus 1. So that will not go any further because those are not similar. They're not the same. They're similar, but they're not the same. 2a plus 1 is not a plus 1. All right. Did I do that right? No, I did not do that right. Because this is not just a plus 1 because there was a 12. I took 6 out of it. That does leave 2. 2 times 6 is 12. So this is 2a plus 1. So these do cancel out. All right. So let me make mistakes. Pop up in the chat or say something if you see me make a mistake there. Don't just assume that it's right. So that just leaves 2a minus 1 on top and 2a on bottom. Now you look at that and it's like, can I change that? You can if you want to separate it as a 2a over 2a minus 1 over 2a, in which case it's 1 minus 1 over 2a. I would take either one. You can do that or you can leave it. They don't cancel out necessarily unless you split it because that negative 1 doesn't cancel out with the 2a. All right, we got a couple more. I'm going to do just one of these so we can get onto our other sheet. Let's do this one. We can factor a 2 out of the top, and that leaves us with a 3n squared plus 4n plus 1, and a 2 out of the bottom, n squared minus 1. Okay, so the 2 is going to cancel out. 2 divided by 2 is just 1, so 1 disappears. So let's factor the top. That would be 3n plus 1 and n plus 1. 3n would multiply to be 3n squared. 1n and 3n, when you distribute that, gives the 4n, and 1 plus 1. 1 times 1 is 1. And on the bottom, this is the difference of squares. So that's n minus 1, n plus 1. These cancel out. 3n plus 1 over n minus 1 is what that simplifies to be. All right, so this is important to be able to simplify this because from the simplified version, we can get a lot of information. So let's look at our other note sheet here. What is a rational function? It's a function in the form of f, I'm going to write this where it's bigger and bolder here. F of x equal P of x divided by Q of x. And P of x and Q of x are polynomial functions. Those are polynomial functions. So it's one function divided by another function, which is what we were seeing on our practice page that we just did, is that we saw this polynomial divided by that polynomial, this polynomial divided by that polynomial. These are rational expressions, rational functions. So steps to graphing these. Now we're going to graph them, but we're going to try to pull information out of that. So first you have to simplify it. And as we already looked at, the simplified function will graph the same as the complex one. Find the x-intercepts by setting the numerator to 0. That's how we find the x-intercepts. For the vertical asymptotes, the denominator is set to 0. And for horizontal asymptote, there are certain rules. All right, the degree, you got to look at the degree of the P and the Q, P over Q. So if the degree of the P, the one on top, if it's larger than the degree of the one on bottom, if this is x to the fourth and this is x squared, well, x to the fourth is larger than x squared. So that will have no horizontal asymptote. None. It will not have one. If the degree of the top is less than the bottom, maybe p to the third divided by p to the fifth, or p to the fourth, or p to the sixth. Q is x to the fourth divided by x to the sixth. The bottom is larger, then our horizontal asymptote is the x-axis, y equals 0. Now, here's the good one. I'm going to write this in a different color. If the degree is the same, notice the equal sign, they're equal. Then it is the ratio of the leading coefficients. And you're like, what in the world are you talking about? The ratio of the leading coefficients. So that means if the top, let's say, we're just going to make this up, x, 2x to the fourth minus x plus 5. Okay, that's our P of Q. That's our top polynomial. And let's say we've simplified it, because that doesn't simplify any further. And down here, we've got 6x to the fourth minus 7. Okay, so when we look at this, the degree for both of those is x to the fourth. Right, that's the same. So these are equal. So the horizontal asymptote is at y equals the ratio 2/6, which really is 1/3. So at y equals 1/3, we will see a horizontal asymptote because we simplify the fraction. Because these are the same, it won't be 0, it'll be at 1/3. So let's put that in and look at that in Desmos real quick.
Are familiar with
Let's minimize that. I'll put it in here. All right. So at the top, what I make up there? I said 2x to the fourth minus x plus 5 divided by, I need to change this f of x or it's going to get mad at me again. All right. Divided by 6x to the fourth minus 7. Woo! Have to zoom way in here now because we zoomed out. See, look at that. It's getting smaller and smaller and smaller. But we said the asymptote's y equals 1/3. So it's saying 0.334, but this says 0.33. That's because it's such a small decimal. It only gives us 3 decimal points, but it gets really, really closer. But it's down to 1/3 is what it's close to. 1/3 is our asymptote. So it will do fraction numbers. Whatever those two, it'll be the same going this direction. See? 0.33876543. As farther it goes, closer it gets.
And that's kind of what is
So basically, just whatever that fraction is, 2/6. If it simplifies, great, 1/3. But it's the ratio. And then the last thing we're going to do, identify any holes in the function. Excuse me. Mr. Brock, you're like, what in the world? A hole in the function? Yeah, that'll be fun. We'll get there in just a minute. So a hole is a point. There's just one point where there's a break in the graph. If you graphed it, you wouldn't graph that point. A hole occurs where there's a common factor. There's the key words. Common factor between the numerator and denominator. So if we want to know where it's at, find the x coordinate, just set the common factor equal to 0. And then to know the y, you just take whatever x you get and put it in the equation, into the simplified one. So let's look at our first graph down here. Graph each function, identify its key characteristics. All right, so the first thing we want to know is what would be the x-intercept? Well, we set the numerator equal to 0. So x minus 4 equals 0. So x equals 4. So we know it's going to cross at x equals 4. That's the x-intercept. X equals 4. Okay, the vertical asymptote. To find the vertical asymptote, set the denominator equal to 0. So x plus 4 equals 0. Subtract 4. X equals negative 4. So that's the vertical asymptote. X equals negative 4. So there's going to be, let's see, there's a ruler. At negative 4, that's going to be that asymptote that it's not going to get, it's not going to touch. It'll get closer and closer. It'll get closer and closer to x equals negative 4, but it's not going to touch that. All right, the horizontal asymptote. Okay, that's our little thing here. What is the degree? Well, this is x to the first degree. That is x to the first degree. Oh, so since they're equal, it's the ratio of the leading coefficients. Well, what is our coefficients? They're both 1s. It's 1x over 1x. So our horizontal asymptote is at y equals 1 because they're the same. So it's going to approach y equals 1, but never touch that. So this kind of tells where our graph's going to be. A hole. Is there a hole? There's no common factor. We got x minus 4, x plus 4, so a hole does not apply. NA, no hole. The domain, okay, the domain is from negative infinity to infinity, except x cannot be negative 4. Because there's a horizontal asymptote there. It's not going to ever touch negative 4. And the range is from negative infinity to infinity, except y cannot equal 1 because it'll never touch that. So now we know where our graph is. Our graph is going to be up here close. It's going to come in real close to there and then go that direction. There, that's where our graph ended up, right? It does not touch those two asymptotes that are right there.
She's set in her ways. She's like,
and right there.
This is the real me.
So we were able to graph that by just pulling all the information out from the equation. All right, let's look at another one. I'm going to take these sheets apart. They're stapled together, but I don't want them stapled together because we want to be able to refer to our notes. All right, let's look at 2x minus 6 over x minus 1.
A little
Here, let's do one that's a little different. Let's jump down to this one.
And she's super
So let's
cute.
do x squared minus 1 and x minus 1 because this factors. This is the difference of squares. That factors to x plus
You're like,
1,
oh, great,
x
what did I-
minus 1
What box did I open right now?
over x minus 1. So these cancel out. That just leaves x plus 1.
I didn't want to get a snake that could eat rats
Because the bottom canceled out with the top one. So what we find, what's the x-intercept? Well, the x-intercept was found by setting the numerator. This is really over 1. Right? Setting the numerator equals 0. So the intercept is at -1.
I'm a big fan. I actually found
-1.
that too.
X equals -1 is the x-intercept. The vertical asymptote, setting the denominator equal to 0. 1 equals 0.
Like a wild
Well,
snake, you know?
that doesn't exist.
Small.
That's
But
not
yeah,
a true
it's
statement. Not applicable. There's not a
that
vertical
little,
asymptote.
like, ring, that little
Horizontal asymptote,
Yeah.
the degree. Well, the degree of the top one is 1. The degree of the bottom one, this is x to the 0 power because there's not 1 down there. So that means there is no horizontal asymptote because if we look at our notes,
They're so
if the
cool.
degree of the top is higher than the degree of the bottom, none.
Fab.
So that doesn't apply either.
Oh yeah.
Not applicable. A hole.
Me too.
So a hole
I feel like
occurs where there's a common factor between the numerator and denominator. We had a common factor. X minus 1
yes, of course they'll fight, but I
existed in both places. So to find the x coordinate, set the common factor equal to 0. So there's a hole.
lied away, but they do not fight me. Like they're just like
So that equals 0, add 1 on each side. At x equals 1, there's a hole.
absolutely.
What is the y of that point? Just substitute this into the simplified function.
Yeah, literally. And like I know
1 plus 1. So at the point 1, 2, this graph does not exist.
water and stuff like that.
So there's a hole at 1, 2,
I'm trying to like swim up in my boat, but it's like they don't.
and the
it's like
domain
they're
is negative infinity to infinity, but x cannot be 1. The range goes from negative infinity to infinity, but the y cannot be 2 because there's a hole there. Now you're saying, all right, what do you mean by a hole? Let's look at Desmos. And we're going to graph. First, we're going to graph what we'd expect, just x plus 1, right? That's what we had. We simplified it to x plus 1. Well, there's x plus 1. There's not a problem with that. It exists everywhere when x is 1. The point 1, 2, that's there because that's just x plus 1. But we're talking about the original. If we look at the original equation, x squared plus 1, put that in parentheses because that's going to be our numerator. And we divide x squared plus 1 by x minus 1.
Preach. Yes, that's so true. I know there's
X squared plus 1. Oh, I'm sorry. It's x squared minus 1. I put the wrong thing. X squared minus 1 divided by x minus 1. Now that looks just like the last graph, doesn't it? Because when we simplified it, it's the same graph. But there's a very distinct difference. This one has a hole in it.
Yeah.
And it's at the point 1, 2. What do you mean? Well, let's see. If we get closer and closer to that point,
They're gonna feed their family.
and we get to the point 1, 2,
Yeah.
it's not going to be there.
Oh my gosh, there's this rattlesnake.
There it is.
I don't know what it's called.
At 1, this is not defined. Notice this is a solid circle until I get to the 1, and now it's a hollow point because if you graphed it on paper, that's what you would need to do. You need to put a hollow circle at 1, 2 because the graph does not exist there. It is undefined. It is undefined. And we look at it and we say, well, it would be undefined because if x equals 1, 1 minus 1 is 0. That means we would be dividing by 0. We cannot divide by 0. Can't have a 0 on bottom. So graphing this, At 1, 2, we would put an open hole, and then the graph would go both directions from there.
They have their place
That's how you
to
graph
put
that
them,
one.
and yeah, I mean,
There's a hole right there.
right, they're-
You don't see it on Desmos unless you zoom in and and hold that
No,
mouse
I
there.
love it,
You
girl.
don't see it. It doesn't look like a hole
Yeah,
because it's defined at 0.99. That exists.
yeah.
That's as close to 1 as we get on
Yeah,
Desmos.
Having
But once you move up to 1,
a
it
course
doesn't exist
that
anymore.
is like,
So
they are
holes are the tricky part. You can't just look at Desmos to tell what the hole is.
considering it,
You
and
can't
you're
do
like,
that
I want something that I
because it's
don't
not going to
think
show you
is
unless
like-
you very slowly go over
I mean,
every
it's
point
like corn snake.
on the graph.
Beautiful.
All right, let's look at another one. Let's keep going down. This one doesn't have a hole because it doesn't really simplify other than taking the 2 out.
Like the pet trade
So
is
let's go down and do some trickier ones
so
here.
perfect.
X plus 5, x squared plus 9, x plus 20. So we need to
But
factor that.
I know. And
So we need
I
numbers that
feel bad,
multiply to be
like,
20 and add to be 9.
you know,
Well, that's easy. It's just 4 and 5, right? 4 times 5, 4 plus 5.
survive in the wild anyway.
So this is the same as x plus 5 over
I got mine
x
at, like, a
plus
small
4
visit
times x
this
plus
was, like,
5.
years ago, but like if
Right, so
I-
these cancel out. So it's just 1 over x plus 4. Remember, when it cancels out on top, everything's gone. It's just a 1 because this simplifies to 1.
Yeah, it's
1 over
just-
1.
I mean, it's just really that
So
long.
1 over x plus
I
4.
mean, there are people who, like,
So what is our x-intercept? Remember, to find the x-intercept, we set the numerator equal to 0.
have their
1 equals 0. Well, that's not a true statement. 1 does not equal 0. So
And
there
they're just
must
like, they
be
just put
no
space
x-intercept.
indefinitely, and I'm like,
And we'll graph it
"Coach,
when we get down here and check our work.
like, I thought you were, like,
Vertical
like,
asymptote. The denominator equal to 0, x plus 4. So the vertical asymptote is going to be at x equals negative 4,
I have a rabbit and a snake.
right? Because x plus 4,
Currently, that's all I have, and I have a kid.
so we'll get there. Vertical asymptote.
It's enough. It's enough.
Horizontal asymptote. Right. Now, we have to look at the original one to see we had an x plus 5, which we got there. We'll deal with that in the middle in a minute because it's going to be a hole. But horizontal asymptote, that's the degree. Well, the degree on top is 1x to the 0 power.
Look for someone who's trying to I
So
love
the
that.
denominator is the larger one. And when the
It's scary out
denominator,
there. Yeah.
the degree of
Go
q, which is the
Go
bottom
with,
one,
like, 10 other
y equals
people,
0
and
will be our
meet in a very
horizontal
public space.
asymptote.
We're ever gonna do that, of course.
The hole canceled out.
Like,
Where did it cancel out?
you gotta bring to protect yourself, but,
X plus 5.
but yeah, no, they do,
equals
but it's
0,
like there are-
so x
yeah,
equals
like,
negative
there's
5.
no mistake, which is always
Negative 5 is
that, like, going after
where the hole is. So we know the hole is negative 5. What's the y? We can just substitute in this easy equation.
that there's
Negative 5 plus 4,
like, I'll just for fun
which is
sometimes,
1
like,
over
like,
negative 1.
what a
So,
weird step for
negative
people
5,
going
negative
against
1
the
is where our hole is.
effect.
What's the domain?
Ooh, yeah.
Negative infinity to infinity, because when we graph it, it's going to go both ways, except x cannot be
I'm here for it.
negative
People will say
5
anything, and it's like,
or
but, you know, well, it's
negative
zero,
4.
so
We have 2. Can't be negative 5, can't be negative 4.
whatever.
I would write that again, like
For, like,
not equal
whatever
negative 4. I
random
just
thing.
kind of
Yeah.
ran out of room. I would write it twice, negative 5, negative 4. The range, negative infinity to infinity. We see that on a lot of these, right? Except for
Right.
what can y
Oh
not
my
be?
gosh, I'm sure it all goes back to childhood
0.
in some way or another, but
All right, let's look at the graph on Desmos. We'll put it on here. Well, let's see. Let's write our parts. Vertical asymptote at x equals negative 4. So we're back to the same vertical that we had
No,
before.
this has been so fun.
So that's our vertical. Horizontal at y equals 0, which is just the x-axis.
Okay. Okay. Oh.
And a hole at negative 5, negative 1. Negative 5, negative
True.
1.
Fair.
So if I graph that,
That's fair.
there's a hole right there. And x can't be negative 5 or negative 4. So it goes
okay.
this way. and down towards that asymptote.
Yeah, tell me.
And then towards the asymptote there, cuts through, and y equals 0 is an asymptote. So it should look like that with a hole at the -5, -1. So let's graph our original equation here. X plus 5, and then the denominator is x squared plus 9x plus 20. All right, that's the graph we just drew. Had the y equals 0 as an asymptote, -4. See, we can put that there, x equals -4. That's an asymptote. And there's a hole, it says right here. So let's look and see. -5.4 over 3. Let's get the -5. Undefined. There's the hole. We predicted it. We had the information to know that. So -5, -1 is undefined. It's defined on either side of it. -497, -508. Just right at that one spot, undefined.
Yes.
All right, we're going to do one more, then I'm going to show you the assignment. Let's see. This looks a little tricky too. Let's see what we got. Excuse me. So 2x, we got a +1 at the end. 1. So 2x times x is 2x squared. 1 times 1 is 1. It's a positive, but we want the middle term to be negative. So if we make both those negatives, so 2x minus 1 times x minus 1 is the factors of that top one. And then here we have x squared, so it's x times x. And we have -12. And we want a positive. So two numbers that multiply together, they're just one apart. So it's 3 and 4 then, right? So we got x plus 4, x minus 3. All right. 2x minus 1, x minus 1, x plus 4, x minus 3. Notice we're not going to have any holes this time. There's nothing in common, and those are all simplified as far as they get. All right, so the x-intercept, the numerator equal to 0. So let's see. 2x minus 1 equal to 0. So 2x equals 1, x equals 1/2. And also x minus 1 equals 0. So x equals 1. So it looks like we're going to cross the intercept at 1/2 and at 1. We have two different places. X equals 1/2 and 1. That's going to be an interesting looking graph. Vertical asymptote, denominator equal to 0.
Okay, but with that being said,
So the vertical asymptote, there's 1 at -4.
And if they have any like gastrointestinal issues,
because of the x plus 4, and there's 1 at +3.
Yeah, they could if they stop. Yeah, so like
Because we set these equal to 0. X plus 4 equals 0. X equals -4. X minus 3 equals 0. X equals 3. Now the horizontal asymptote, the degrees, they're both x squared. These are the same. The same. They're equal to one another. So when they're equal to each other, it's the ratio of the leading coefficients. 2/1. This has a coefficient of 1. So our horizontal asymptote is at y equals 2, because that's what 2/1 is 2. Is there a hole? No, these are all different. None. No hole. And the domain. Okay, well, the domain is going to be interesting. Let's see. -infinity to infinity, except x cannot equal -4 and x cannot equal 3.
That is so dumb.
Put a comma between
so
those.
funny at the same time. Oh my gosh.
All right,
I love it.
and let's see. There's no holes to deal with. The range goes from -infinity to infinity. Notice we're always doing -infinity to infinity, but we have to say where it's not defined at. Y equals 2. Y cannot be 2. All right. Well, let's graph this thing, see what it looks like, because it's pretty tricky. So the numerator was 2x squared minus 3x plus 1. Okay, and the denominator was a 2x squared plus x minus 12. Okay,
It's probably the
now let's compare this. That's a rather tricky looking graph. Let's see. Open this up where we see it a little better. All right, we said we had two x-intercepts. One's at 1/2. There it is, 1/2 and 0. And the other one's at 1. So there's our two x-intercepts that we had on there. Said there's a vertical asymptote at x equals -4. I'm going to put those on there so we can see them. X equals -4. And there's another one at x equals 3. Now this, interestingly enough, looks like it mainly just affects the bottom part of the graph.
And it's funny too.
It is an asymptote, but it's only for the bottom part of it.
There was a period in my life where I was like,
I have those backwards. No, that's right. That's what I have.
So I worked.
So those asymptotes are as they go down, they'll get closer and closer to that.
And they did like bird banding.
Up here,
and, like, educational stuff, and like
it crossed them over and it's doing something different.
Like bird nerds essentially who like talk.
And then we're supposed to have
bird
a
nerds
horizontal
talk
asymptote at
about
y equals
birds
2.
who, like, you know, how to recognize, like, you know, at least the
It's
local
not at
bird
y equals 2.
calls, you know, and it was
Unless it's getting bigger as it gets down here.
It was so cool.
It looks like it's a
So,
y equals
like,
1. Now what's,
back when
oh,
it's
wait a minute. The bottom there was not a 2. The bottom was just an x squared. That changed everything. Okay. I put the wrong equation in. It's just x squared plus x minus 12. Okay, now we can see the asymptotes are working right.
They are.
See the asymptotes at -4 and +3. It's getting closer and closer at top and bottom. And the asymptote at y equals 2. Now this is interesting. On this one, it stays above it.
Yes.
This
Oh, and they're-
one,
yeah, they're, like,
it
locked
dipped
in,
below
like,
it,
up there.
but then it's coming back up towards 2.
Fancy camera, like, whatever it is, but they're just like, they're so into it.
Keeps
Like,
wanting to put
oh
me
my
on the
gosh.
purple one.
You cannot
There we
tell
go.
those people that birds aren't
Then it's
real.
getting closer and closer from the bottom side. So it's interesting how
They would.
some of these equations, when they get really complicated equations, have interesting things. But those are the asymptotes.
Oh my gosh.
3 asymptotes.
Um,
And we had the x-intercepts that we found down there. Let's see. And there was no holes. So there's no holes that we have to check. All right. Well, you can guess what your assignment's going to be. It's going to be figuring out this stuff over here. So let's look at it.
there is a video. I want you to see that.
All right. Pull it up here.
Okay, hold on. So there's this documentary.
Yay. Okay. So
On Netflix.
really you have 3 problems
Amazing.
to do. I give you the equation. I give you the graph.
It's just like,
Notice this has slant asymptotes, but we're not talking about slant asymptotes. But there are such a thing
yeah, just the way
as a slant asymptote. So this one, the x-intercept, you got to choose where's the x-intercept. I'll give you multiple choice on that.
Okay.
The vertical asymptote, you have to type that in. If it doesn't exist, you put it in A. Horizontal asymptote, y equals. If it doesn't exist, put in A.
And then I'll let you.
The function as a whole at one of these x's, x equals -3, 0, or 1, or the function doesn't have a hole. Tell me which it is. And then type the domain and range. So that's for this function. After you get that, you have another one with a new function.
It's always
Here's your new function. There's the graph. Fill in the information.
It's not just David
And then
Attenborough.
one last one here.
Like every time I look
Remember,
up
you got to
a
factor
video
that.
about, like, zoology or-
It factors nicely
lots of
just
stuff.
into an x, two x binomials,
Every time.
and the same 6 questions to fill in on that. So that is the assignment you have for this week. Just 3 problems that you've got to give me the asymptotes, the x-intercept, any existing holes in the domain and range. So there you go. Any questions?
You're right about that.
I'm going to post these notes in Google Classroom. Since I've got them all written up here, I'll take pictures of them. I'll put them in there with the blank notes. And
Oh my gosh.
there you go.
Okay, here- this
I
is
will
a-
let you guys go and
Okay.
tackle the day.